Let's solve another problem which would appear to be a rather simple problem. But without our knowledge of the principles of entropy, we would not be able to solve this problem as it is given. Refrigerant 22 enters a compressor operating at steady state, a saturated vapor at 10 bar, and it's compressed adiabatically in an internally reversible process to 16 bar. Ignoring kinetic and potential energy effects, determine the required mass flow rate of refrigerant in kilograms per second if the compressor power input is 6 kilowatts. Well, let's lay out our storyboard. We'll begin with a schematic. We have a refrigeration compressor where R22 comes in at state 1 and exits at state 2. And as I'm showing our conventional definitions of positive heat transfer and positive work. It doesn't mean that these numbers are going to be positive in this problem, but for any schematic, I would generally draw that positive work is the system outputting work to its surroundings, and positive heat transfer is heat transferring energy into the system. Let's look at the given data. State 1 is fully defined. It's R22 at 10 bar and it's a saturated vapor. Now state 2, we're given a pressure of 16 bar, but that's all we're given. So state 2 at this point is not fully defined. We were told that the compressor input power is 6 kilowatts. So I can write that W dot is equal minus 6 kilowatts. Going back to our convention of positive work. Let's model this system. These assumptions are going to be important for us to be able to solve this problem. We're dealing with an open system operating at steady state. We were told to ignore changes in kinetic and potential energy. And we were told that the system is adiabatic, which means Q is 0. We were also told that it's an internally reversible process. And so without irreversibilities, the entropy production will be 0. Now here's where our understanding of entropy is very important. We were told it's adiabatic and internally reversible. Well, remembering our lesson on isentropic processes, an isentropic process is adiabatic, it's internally reversible, and it's a constant entropy process. In other words, delta S equals 0. And also recall that if we have any two of these characteristics, then we also have the third one. Well, we were given two. We were given it's adiabatic, we were given that it's internally reversible, and given our knowledge of isentropic process, that is enough, having these two characteristics, to know that it also has the third characteristics that delta S is equal to 0. It's a constant entropy process. And we want to find the mass flow rate in kilograms per second. So let's draw a TS diagram of this process. State 1 is at 10 bar, so it sits on our constant pressure line of 10 bar, and it's a saturated vapor. So state 1 sits here. State 2, all we know is that it's somewhere on this 16 bar constant pressure line. Well, this assumption that we made here, that this is a constant entropy process and delta S equals 0, allow us to recognize that state 2 has to be directly above state 1, so that the entropy at state 2 is the same as the entropy at state 1, and that now fully defines state 2. So let's find some state properties. We can go to the R22 saturation table at 10 bar, and because we have a saturated vapor at state 1, we know that H1 is just H sub G, and the table tells us that that enthalpy is 257.28 kilojoules per kilogram. Likewise, S1 is S sub G, and it has a value of 0.8952 kilojoules per kilogram. Now, for state 2, we have two properties defining state 2 now. We know its pressure is 16 bar, And we know its entropy is the same as the state 1 entropy, so its entropy is 0.8952 kilojoules per kilogram. So we can go into the superheat table at 16 bar and look for this entropy value. And we find that it sits between these two rows. The first row has a temperature of 41.73 degrees C. The second row has a temperature of 50 degrees C. And both of these rows have an enthalpy given and an entropy given. And we know we're sitting in between these two rows. So let's interpolate. As you know, I like to find an interpolation factor independently as my first step in interpolating. And my F value here, as I call it, would be 0 for row 1 and 1 for row 2. And the calculated F value tells me how far between these two rows I am. So my interpolation factor F is just S2 minus the entropy value in the first row, divided by the entropy value in the second row minus the entropy value in the first row. So I can plug in all those numbers, and I get an interpolation factor of 0.9258. So you can see we're much closer to the second row than we are to the first. Now let's calculate the enthalpy at state 2. It's the enthalpy value in the first row plus my interpolation factor times the enthalpy value in the second row minus the enthalpy value in the first row. I'm plugging in all those values. I get a value for H2 is 268.58 kilojoules per kilogram. Now I can write and solve an energy balance. I know dEdt is 0 because it's operating at steady state. And that's equal Q dot minus W dot plus M dot times H1 minus H2 times the change in kinetic energy plus the change in kinetic energy, or excuse me, potential energy. So we're neglecting kinetic energy, we're neglecting potential energy, and we were told that this is an adiabatic process, so Q dot is 0. That simplifies our energy balance considerably, and rearranging, I calculate that W dot is the mass flow rate times H1 minus H2. Well, my unknown is the mass flow rate. So that's simply W dot over H1 minus H2. So the mass flow rate is W dot, which was given as a minus 6 kilowatts, divided by H1 minus H2, and we have developed values for that. And I recognize that 1 kilowatt is a kilojoule per second. And so I get a mass flow rate of 0.531 kilograms per second.